All right, hello, hello, hello. This is the recording that I am trying to do for the first time. Hopefully, it goes well. This recording is brought to you by the letter W. It is W because I am sitting in the track and field stadium at Ohio Wesleyan, broadcasting this live to you via some transportation or transportal model to your ear through the internet. Just as a heads up, we will have a quiz over this material, including this material and the rest of Chapter 8 on Friday. It will be an online quiz, and it will last, as you can see on the screen here, from 6 a.m. until 8 p.m. The quiz will obviously cover Chapter 8, but we'll get to that later. Okay, so what is important to note right now is that
Lane assignments for Section 2, Lane 2, Daniel Samuel.
What's important to note is that at time to time you may hear some screaming and yelling in the background, and that is because, again, I am at a track meet. So what's important to note for this upcoming chapter is that this is about system of equations, and we will cover sections 1, 2, 3, and 4. The chapter in and of itself is 4 sections long, and you can see there where we'll learn some techniques, one called substitution and the other called elimination. And this is an introductory conversation that I want to have, where I want to ask you to take notes and come to class with questions, because we will cover substitution in class. So chapter 4 or section 4 will be about applying those to different problems that you run across. Now, system of equations, what are those? Well, those systems are a system of equations is a two or more variables or two or more linear equations that deal with functions, and we can determine whether or not they are whether the systems actually work out. And when we're going to use language like consistent and inconsistent, and we'll look at whether or not the systems are dependent or independent of each other. And what we'll do is look at multiple variables, maybe 2 or 3 variables in a system to see how they work out. A lot of times we look at somewhat more complex problems than just the simple Peyton cut hair type of situation. We can add in some wrinkles to say, well, if Peyton cuts hair and someone else sells neckties, is there a point where those two systems either are where it is better to maybe sell neckties, or is it better to cut hair, and looking at maybe when those two systems come together. So having said all of that, let's go right into what a solution of a system really is. It's a place where the two equations have one solution, and it will be an ordered pair. An ordered pair will look obviously like an ordered pair. You will have an x and a y value, where both of those equations, where the equation will both, this value will be true for both. The same thing can be said for if we were to graph that equation. If we graph the two equations, the place where those two graphs cross or intersect would be a point, and that point would be the place where those two things are solutions. So let's look at this particular set of equations that we have here. Well, if we were to graph these two, and I'll set it up very quickly, hopefully, to show you that this one is y minus x is equal to 1. We can then graph this using the slope-intercept form by adding x to both sides. And we end up with the equation that looks like y is equal to x plus 1. And then this one here is y plus x is equal to 3, and we can subtract x from both sides. And if we do that, then we end up with y is equal to negative x plus 3. Now, if we graph both of these equations, we would figure out very quickly that the slope for this one, let's change colors really quickly. The slope for this equation, let's go with it. The slope for this one is 1 over 1, and the y-intercept in this case would be the 1. The slope for this one would be negative 1 over 1, and the y-intercept in this case would be 3. So what does that look like? Well, we would anchor here and then go over 1, up 1, each time and then draw a line. And then in this case, we would anchor here at 3 on the y-axis and then go over 1, down 1 for each time. So let's look and see what that looks like. If we were to graph that, it would look something like this, and we would find that the common solution for both of these is this point here, is the point 1 over 2. Now we can figure that, we can look at this through another lens, or at least a more critical lens, by saying that if we plug this value in for these two numbers, it will actually give us an equal symbol, an equal statement. So let's see, if this is x and this is y, we know that if we put x and y here, we would get y is 2 and x is 1. Does 2 minus 1, well, that equals 1. So this makes this a true statement. The same can be said here. This is 2 plus 1 is equal to 3. Well, 3 equals 3. This again is a true statement. So this point makes both equations true, and it is a place where these two equations cross. All right, simple enough. So now, the point of intersection that they both have is what I just explained there. We can check that just like I did with both equations. So now if we were to solve these graphically, now we can use the slope-intercept form once again, knowing that this is our, that 5 in this last equation is our y-intercept. So this is our y-intercept, and this is our slope here. Our slope would be, for this equation, our slope would be -3 over 1. And our y-intercept would be 5, and this
Next
one would
event will be the women's 200 meters.
This
we'll
one
have
would be
6 heats of that.
3 over 1 would be our slope, and our y-intercept would be -2.
Run, followed by the men.
Now, what do we know from? Now, what do we know for certain about these two equations? Well, we know from the last section that we worked with. We know that these two equations have the same slope but different y-intercepts. So that means that these two equations, f of x and g of x, are parallel lines. That is the notation for parallel, these two lines. So these two lines are parallel. So that means they will not have a common place where they will cross each other. So graphically, we already know that there is no common solution for the two of these. So if a system of equations has at least one solution, it is consistent. So our very first problem was consistent. The second set of problems that we worked on were inconsistent. The two parallel lines were inconsistent because they never cross. And so if it doesn't have a solution, it's inconsistent. If they have at least one solution, then it is a consistent system. Okay, make sure you note that make sure you denote that in your notes. Somehow making sure that you really make a point and effort to make sure that you understand these definitions. And if you think about the parallel and perpendicular line scenario, it fits right in that same conversation. Okay, so let's move on. We want to solve these graphically. And now if we want to solve these graphically, let's see what that looks like. If you can look at this particular set of solutions here, or look at this graph here, you can say that this has one solution, and therefore the graphs intersect at one point, and it is independent. So let's go back and just make sure that we clear up anything that's going on. If two systems and two variables have infinitely many solutions, or has infinitely many solutions, they are dependent. If it has one solution or no solutions, they are independent. So looking at these two graphs, we're going to graph these, and I'm going to save you the time of looking at me do the problems out. But essentially, what I'm going to do is change these to slope-intercept form, and this is what it looks like. And as you can notice, they are independent because it has one solution, and they are consistent because they have a particular solution. So, if we have two parallel lines, what do we know about those two parallel lines? We know that it has no solution, but it also is inconsistent because it does not have any solutions whatsoever, and these two things are independent of each other. So let's go back just to be sure. I'm going to flip back to this definition here. Actually, I'm going to go to here. Consistent. Consistent means at least one solution. Inconsistent means no solutions. And here we have dependent means that it has infinitely many solutions, and one solution or no solutions is independent. So that means that this system is independent and inconsistent. So infinitely many solutions, that then goes to this idea of the systems being consistent, but they are dependent on each other. Okay, so that wraps up the introduction for section 1. I'm going to ask of you to review this information, and I'm going to put up on the board on Monday morning or Monday afternoon when we get to class. I'm going to give you some problems. I'm going to ask you to make sure that you can classify them under the banner of consistent, inconsistent, dependent, or independent, and whether or not they have one or infinite or no solutions. Those are the three things, or the three indicators that I'm going to be looking for. And for the most part, I'm going to ask you to graph using the slope-intercept form, and sometimes you may have to change them from the standard form to slope-intercept form. So hopefully this works out well, and I hope to have you guys work through this on Sunday night, and I'll talk to you on Monday morning. Thanks.